as well as the Skywarn coordinator for York County. And with severe weather season right around the corner, it's a good time to revisit our Skywarn and severe weather presentation. So I'm glad you guys could join me for that this evening. So we'll start with a quick recap of the radar equipment. As you see, the WSR-88D is the standard Doppler radar that's deployed by the National Weather Service, as well as the Department of Commerce, the Federal Aviation Administration, and the Department of Defense. They transmit at 750,000 watts at 2.8 gigahertz in the frequency. That radar system is older than I am. The caveat there is with the Service Life Extension Program, SLEP, what they do is they test and deploy new technologies to update the older equipment to maintain their serviceability. There's a picture of the actual antenna itself without the radome in place, being hoisted in there for a new radar install. And the way the radar works, if you use your favorite radar app, whether it's Radar Omega, Radar Scope, or there's a few others out there, you can see what mode the radar is in. And the most common mode that you'll see is clean air mode. And what you see is these are called volume coverage patterns, and it gives you an idea of how the radar is scanning. So the beam comes off the antenna at a series of elevations, and that's what provides you the depth of a storm cell or of a storm system. So it starts at 1/2 of a degree and progresses up to 4.3 degrees in clean air mode. That's to get an idea. It's a long range to kind of see what's going on as far as reflectivity and other products downrange. When there's precipitation in the region or within the confines of the radar, they can put it into Precip Mode. And what Precip Mode does, you can see it increases beyond that 4.3 degree horizon all the way up to 19.5. And what that does is it gives you the ability to look at taller objects, being storms or gust fronts, things of that nature, so you can see up nice and high. And again, with the Service Life Extension Program, they've added some features like SAILS, or Supplemental Adaptive Intra-Volume Low-Level Scanning, where what you end up with is a scan at 1/2 degree, 1.5 degree, 2.4. It'll come back down and do a scan of the lower levels before it progresses through the coverage pattern. What that does is it allows you the ability to see changes at the lower levels without missing those changes due to having to scan the higher elevations first. There's also a mode they can use where it doesn't have to scan the entire coverage pattern. So if you have a storm system that's either far enough away that it's not quite as tall to your beam, or if it's up close but it's not tall enough, it doesn't have to go all the way through all of the coverage pattern. Once the beam identifies that there's no more scatter above a certain elevation, it'll come back down and start over. Again, with radar products, up here in the top left, you'll see a reflectivity image. This is what you're used to seeing. This is what your news stations are going to show you. For the most part, it's the most common radar product that you would consume without getting into the severity of it. This is a very good indication of rain, the density of clouds, and the particular scatter inside those clouds, where the heavy rains are obviously denoted by more aggressive coloring. To the top right here, you'll see a velocity product. What the velocity product shows you is wind speed relative to the beam of the radar. We'll get a little bit more in depth on that here in a minute. Down here you have a differential reflectivity, which shows the difference in the reflectivity of your X over your Y. It's a good way to spot things like hail and some other scatter that we'll talk about, or some other hydrometeors that we'll talk about here in a minute. The correlation coefficient shows you the consistency of that scatter, or of that object that the radar is reflecting off of. Raindrops tend to be very similar as they fall, and they're more uniform, and you note that there's a much greater consistency in the correlation there. This here, what you're looking at, is a debris ball, because you can see that it's a very low coefficient of correlation, which means the beam is picking up things that are very dissimilar in size and shape. In this case, you're talking about organic debris, think tree branches, trees, things of that nature, potential building materials, pieces of buildings that have been impacted, things that are just general debris in that ball there. And with these four images, or actually predominantly these three images, you can tell that that is a tornado signature. So we'll look at this line here that's approaching Indianapolis. This is a reflectivity image. And you can see this is a very standard quasi-linear convective system. We'll talk about that in a second. As this is moving west to east, you can see the pockets of very heavy precipitation with some gaps in there, a very strong reflectivity gradient, which is the distance, difference over distance, basically. So you see here you have no reflectivity, and then it goes very quickly from the blues and greens to yellows, reds, over a very short geographic distance. That's a very high gradient. It's indicative of a pretty strong front here that's not allowing precipitation to form to the east of it. This is that same line under a velocity product. You can see the beam. This is your radome here, the Indianapolis radar. This is the line that the beam basically creates there. And when you look at it, you'll see that red colors indicate winds moving away from the radar. Green color indicates winds moving towards the radar. So in this is your boundary here. This is all moving in the same direction, even though the color changes. And what you find with things like this, these pockets of very high, very bright color velocity product, those are areas of high winds, high pockets of wind. You can see that it's all generally going in the same direction, which is west to east, and you don't see a whole lot for contrasting colors. You don't see a lot for a big tornado threat out of a line like this as it stands here. This is a good view of your correlation coefficient. It's showing, in this case, pockets of what are hail, or could very well be hail. As you see, these darker pockets here indicate that the hydrometeors, or what the beam is reflecting off of, is much more uniform. Ice generally forms, it freezes in its atmosphere, and as it falls, it pretty much stays the same shape and size as relevant to its counterparts. So you see that it's identifying areas of very similar precipitous in the form of hail in this case. We're going to talk about some of the severe weather generators. Pulse storms, very, very common in our regions, the greater South Carolina, North Carolina, if you want to call it as far out as Dixie Alley. This region of the southeast U.S., pulse storms are very, very common. The kicker here is there's very low shear in the atmosphere. Shear is both a blessing and a curse, in that shear, or changing of direction of the wind in the atmosphere, can shear the tops off of storms, which allows them the ability to progress by having their outflow separate from their inflow. In this situation, that doesn't happen. So what you have is you have your upflow, your updraft, which rises in height. As it rises, you get that convective, that motion that causes the precipitation to grow. And you see these all the time in the summer. You get the heating of the day causes the lifting. You get these big storms that eventually reach a point where they become too heavy and too dense, and they rain, or they precipitate. These are the storms that you see that fire up, move on, fire up, move on, fire up, move on. They pop up, they disappear. They pop up, they disappear. You might get an inch of rain, but your neighbor across town didn't get a single drop. This is a good multi-cell cluster of pulse storms in this case, where you have good loft, good precipitation, but the storms aren't really moving across great distances. They're not severe by any nature. They can be, but oftentimes they stay sub-severe. They may produce a little bit of hail, which would generate them as a severe storm, but that's fairly rare, generally because the temperatures required to create this environment would make it very difficult for hail to reach the ground. Your classic supercell thunderstorm, you have your start of a rear flank downdraft. This system here, this is called a hook echo. It's very easy to identify because you have this giant area of precipitation. That's your outflow from the storm itself. This is your inflow notch here. This is where you have that strong inflow that's lifting. That is your hook. That is generally where your tornadic activity is. This is your pockets of very heavy rain and potentially hail. And then as you get farther away, you notice the reflectivity gradient is not as sharp. So you have areas of very heavy rain, very moderate rain, very light rain, and then none, if any, or very, very light, if any, farther away. This is a good example of what I was talking about earlier with the shear. As this is being lifted, it reaches a point in the atmosphere where this shears off, and it pushes the tops of that storm back down to Earth in the form of this precipitous here. Or this precipitation rather. This allows this storm to be basically self-sufficient. It doesn't choke itself off very easily because you have the inflow separate from the outflow. So you have a situation where it will continue to grow because it's not choking this off. When you have an environment with very little shear, this will fall into the outflow of the storm and choke off that inflow and cause the death of the cell. One of our greatest severe weather producers in the southeast is the quasi-linear convective system. It's frequently it is frequently referred to as a squall line, and you can common when we have a weather system that moves in and pushes across the area very rapidly. You can start to see these events take place where you have a lot of reflectivity here along a line. Generally there's some precipitous out front of that line, but when you come into the velocity image, you can see this is all moving towards the beam there. And you can see very clearly the front. What you have is pockets of very, very heavy winds and very high winds moving east. And then you have these pockets here where there's not a whole lot of wind because the front hasn't reached that yet. This can spin up some tornadoes. Some pretty devastating tornadoes come out of QLCS systems. They're definitely the most common down here that I've found compared to, say, supercells and things of that nature. National Weather Service severe thunderstorm warning criteria. Winds 58 miles an hour, 1-inch hail, that can be radar indicated, or a tornado, or funnel cloud, radar indicated rotation, things of that nature. It's very rare to see hail of 1 inch in diameter reaching the ground in this region, again because of the temperatures that we have. And then the measured wind speed of 58 is pretty high up there as well. So the severe thunderstorm progression used to have very little room to warn people about storms that were approaching that could become severe. So they fixed that with the special weather statement. You'll see them put a special weather statement on the storm. Watch this storm. It could be strengthening, but that way 3/4 inch hail is still very serious hail. It's just not yet severe. So to prevent that from becoming a life-threatening situation, they warn people ahead of time with different warning criterias. The limitations. So you have what's called beam scatter, and this is a perfect example of this. You'll have to forgive the quality. This was a mobile screenshot. This cell here, this is a correlation coefficient image. You see the radar has indicated, the computer program has indicated that there's rotation with some of the cells here. All of your radar applications are going to have tornado vortex signatures, potential for rotation, storm tracks, things of that nature, including hail size. Those are all computer generated based on the information that it's getting from the radar products. So in this situation, there was some rotation here, which was observed that generated this red box here, which is a tornado warning. this tornado warning inside this severe thunderstorm warning, this severe thunderstorm warning, this one you can see this is a line. This was a very big QLCS that came through. But the problem was this storm here was so tall and so dense that the radar beam had a hard time penetrating that storm, and that led to this striation here that shows you that the beam sometimes can't penetrate all the way through that to get good returns of what's on the other side. In this situation, this is Greenville-Spartanburg's radar. If you switch to Columbia, you might be able to get a better idea of what's on this side of it, or even Peachtree City, Georgia. The time of the scan, as we talked about with volume coverage patterns, sometimes it can take 3 to 5 minutes for the radar to go back to that lower elevation to get you a good scan. That's why sails is so important. When they put the radar in sails mode, they can see low-level changes faster. But even on the fastest of settings, you're still a few minutes away. And with supercells, it's not as serious because, yes, things change quickly, but those changes don't come and go very quickly. A supercell, that's you can kind of gauge where it is in its life cycle, develop a plan for how it's going to move, and then by the time the radar comes back, see what's changed, and then graph those changes. In our situation here with a QLCS like this, storm systems can go from sub-severe to tornado on the ground, causing damage, to sub-severe in a matter of a few minutes. With the speed that these systems move and the rate of change, it's really hard to identify what that system is going to do 4 or 5 minutes away, which is why things like sails are so vital to being able to get data real time, or as close to real time as you can. Elevation over distance. I know if you've sat through this presentation before, we've talked about that one, where when the beam from Greenville-Spartanburg comes over top of our clubhouse here in the south end of York County, that beam's at between 7,000 and 9,000 feet. I've never seen a tornado at 9,000 feet. Typically, tornadoes are 0 feet, and the radar can't see the ground because the earth is not flat. So with that being said, the radar can only see 7,000 plus feet above us. It's really hard to see what's going on the ground. That is why the importance of skywarn spotters, trained weather spotters, the news media, social media has become huge for this. Everybody's carrying around a 4K camera now, or at least 1080p. And when you see severe weather that's taking place, most people pull their phones out and start recording that. Post that to Twitter, post that to Facebook, post that to your social media of choice, and tag the Weather Service in it. That will give them an idea of what's going on at ground level so that they can use that data to then further their warnings. Temperature, that's a big one with freezing level. Again, with hail, right now I think it's in the 40s outside, so if for some reason we had hail, there's a good chance it might reach the ground before it melts. When it's 95 degrees outside, depending on where that melting layer is, if you have hail that high up in the atmosphere, tens of thousands of feet, and it starts to fall, it has to go through that melting layer, which might be, again, thousands of feet in the air. The odds of that precipitous making it to the ground in a frozen state is very limited. So side of that is snow. A reflectivity image will not necessarily show you rain versus snow. Again, that's a computer-derived image that your weather service or that your news media or your radar app are showing you, because the beam can't tell the difference. Again, if the beam's at 7,000 feet, if it starts to snow at 5,000, you're not going to be able to see that. So that's where you take what the radar can show you and augment that with the data that we have available. I'm going to touch quick on complacency. A favorite story of mine, I used to be assigned to Charlotte Douglas International Airport. My office was this tiny little room with no windows, one door, tiny. And we heard this god-awful noise. And there's 4 of us in there. We all look around at each other. Man, is it raining? I don't know. It sounds like rain. Well, the jetway was, or the hallway that connects two of the terminals was only a couple 100 feet away. 3 out of the 4 people in their room pulled out their phones and started trying to load their radar app to see if it was raining outside, rather than walking over and looking out the window. All too often we find ourselves addicted to the technology and afraid to go look outside. My favorite is when somebody calls in that a wall cloud is rotating, but they're driving down the road at 75 miles an hour. How are you observing that rotation? You can't observe rotation if you are moving. You need to be stationary to observe change in a moving object. And a lot of times those things get overlooked because of the complacency of, that storm has a warning on it, that must be rotating, I am seeing rotation. Take a few minutes, stop, get out and look at it, and then make that determination if that's a rotating system or not. If that's rain or if it's hail. Is it hail? Is it sleet? Is it freezing rain? We don't talk about that a whole lot in this presentation, but feel free to reach out to me with any questions on that, and we'll cover the difference in that. So we're going to get into some case studies here. You'll have to forgive some of the imagery is kind of old. We're working on fixing that this year. This was June 23rd, 2019, summer field day. For those of you who are not amateur radio operators, field day is a great opportunity to get with your local groups. The idea is to go to a location, deploy equipment, get on the air, and operate radio equipment from an emergency setup standpoint or an emergency communications perspective. So as you see, we've got a bunch of antenna setups in this big field here. This is Steve's camper. There's a big tent here. He's laughing in the back because he knows where this story is going. This is the satellite communications trailer and a very, very pricey van here. I don't know how you guys are doing field day, but we had gigabit internet up and down, Wi-Fi, blanketing the campsite, satellite. I mean, we're always taking applications, ycars.org. There's a lot of really expensive equipment going on right here. And I was up the hill here in the bus, working to get on the air station, also monitoring the radar. Again, forgive the imagery, it's very old at this point. So the star is about our relative location in York County here. And they put this big old severe thunderstorm warning up, and the severe thunderstorm warning was for these cells, I guess, down here, this line down here. And this line was, obviously, it was severe. Though this is being a velocity image, you can't really see the details on the reflectivity, but this was a severe line that was moving through. You'll notice no severe warnings up here. It's all over here. And the warning specified Cherokee and Northern Union counties. They extended it for us because this was coming down in a more southeast motion. But this here was what caught my eye. We'll keep an eye on it. A few minutes go by, and that's what that velocity image looked like. This was one scan. This was scan 1. This was scan 2. That was your change from the time it did its first scan to its second scan. This velocity product here is terrifying. This here was significantly worse. It's what got everybody's attention. And we'll talk about that from the complacency aspect of things here in a minute. This is what got everybody's attention. As far as the National Weather Service, as far as the Skywarn net that was currently in place because we were under severe thunderstorm warning. I saw this right here, this north portion on the radar, and called our site safety guy who was like, hey, I was like, hey, listen, we've got some weather moving in. It's pretty serious. And I'll never forget, he looked at me and said, what makes you think that? So I called Ted with the communication trust. Ted, put your dish up. You need to start securing stuff down there. Everybody that was downrange there in the field day setup, they were all on the radios. They had their headsets on. They were making contacts, having a good time. Got through to somebody who wasn't terribly busy and said, you guys need to start securing your stuff. Well, what makes you say that? Well, when we looked off to our general northwest, that's what we observed. And looking at it, it wasn't rotating. I wish I'd have gotten a video, but the picture I'll just have to do. It was not rotating, so it was not tornadic in nature. But with that lowering, you can see very clearly, you have your line, your quasi-linear system there, and then you have this breakthrough. That is this pushing through that line. Where these systems become tornadic is where this pushes through this line and this part recedes and it creates some rotation. Excuse me, that is not what took place here. Shortly after this photo was taken, we lost, I think, one of the antennas, Steve's awning. There was a bounce house party thing going on up the hill from this photo to our left. There's a kid's birthday party. They lost everything. We managed to get most of the tents to the ground, most of the equipment staked down. We didn't lose a whole lot. But we estimated the wind speed coming across that field at 85 miles an hour. That was just with some of the damage to the trees. There were trees down. And it put us down for quite a few hours trying to get some stuff back. I think we were down 2 or 3 hours trying to get everything back up and running and operational. So that's one of those situations with complacency. Everybody was concerned with what was going on down here. From the regional level, this was the bigger threat because the National Weather Service and WSOC TV and all of our meteorologists that are monitoring these situations, they don't know that we have an event going on here at this time. That's not on everyone's radar, no pun intended. So it's the concern is this area of seriously increased velocity, which is what generated this severe thunderstorm warning. I don't want to say this went unnoticed, but you can see how fast that developed. This is probably a period of 3 to 5 minutes, how fast that system developed and caused significant damage. And that's the purpose of this entire presentation, is to give you the baseline tools you need to look at an image like this, make a rapid decision that could potentially save you and your family a lot of headache having to deal with severe weather. If you're out at the park and you look up and you go, man, that cloud just looks weird, and you look at radar, you can use those tools to say, okay, this is what this is doing. Again, mobile. We were down, actually Steve and I were at we were down at Chester State Park doing a Parks on the Air activation for this one. You can see my buddy here. This is real time. My buddy here, hey man, what's going on? What do you mean what's going on? My phone just went off. They said a tornado. Well, obviously heed the warnings that you're being given, but let me take a look. So in this situation, you can kind of see an inflow notch starting to form here. If you're looking at just a reflectivity image, there's no indication that this is a tornadic cell, because it's not a Midwest supercell. You didn't see it coming 20 miles away. You didn't see huge hook echoes, big inflow notches, the rear flank downdraft. You don't see those typical signatures here. You do see a little bit of an inflow notch starting to form, but if you didn't know what that was, this doesn't look tornadic on its surface. This is a tornado vortex signature that radar scope put on that cell because their algorithm determined it was tornadic in nature based on the information here. If you switch to the velocity product, you can see why. What you're looking for here is what's called gate-to-gate shear. And the distance is 1 pixel. What you're looking for is more than 100 knots of shear across 1 pixel. That is enough to generate a tornado warning on a cell. So what you have here is extremely high returns here and reasonably high returns here. They butt up against each other. This big, bright, single pixel gate here is indicative of a funnel cloud, potentially a tornado. Excuse me, the difference being a tornado is a funnel cloud that's on the ground. We're going to look at another one. This was from just last year. My plan was to give this presentation in March of last year, and then they hit us with tornadoes in January and February, so we had a really busy March getting some data together. This particular screenshot comes from National Weather Service report database that they have. We're going to be using this a lot coming up for next year's presentation on this topic. But you can see here, this here is a very broad area of strong winds. You can see this is a damage report of damaged trees. So this caused some damage, this caused some damage, this caused some damage. But you notice none of these that caused damage are inside this tornado warning box. That's because the tornado warning wasn't for this. The tornado warning is for this right here. Because this is contrasting 100 knots gate to gate. This is an area of very tight rotation. This could very well be rotating, but this is a big broad area of rotation if it's rotating at all, if it's not just high winds pushing through. So this generated a tornado warning on that storm there. This line, this was a quasi-linear convective system. Again, you can see the big large area warnings that encompass multiple counties across a whole line. These are cell markers that the application put in place. This one's indicating there's some, I believe that's a hail marker. Again, those are computer algorithms that generate that information. You can see here this really tight area of rotation here. There's your gate-to-gate shear that generated this tornado warning here. This area of gate-to-gate shear here generated this tornado warning here. And the strength and speed of this system is what deviates how far that warning extends. You can see this here is just approaching. It's right on the south side of, looks like it's coming into York County from the Chester County area. That would go on to produce I believe it was an EF2 or an EF3 tornado. I believe it was a 2 that took North Central High School in, I believe it was in Cherokee. That was this system down here, Kershaw rather, pushed to the northeast, came up and did some pretty significant damage to the school. This one, just over a month later, this tornado here, you can tell with the gate-to-gate shear. Again, these images are terrible. The reason this image is terrible is this is not from a National Weather Service WSR 88D. This is actually from Charlotte Douglas International Airport's Tower Doppler, which they feed into the same network, so you can see there's good overlay there. There's some obstruction to their north-northwest. That's what causes this gap in the beam here. But you can see there's a good area of rotation there, and this storm moved almost due east. This is a different one. This is the Spartanburg tornado. No, this is not the Spartanburg tornado. This is a southern Spartanburg into Cherokee County tornado. Again, you see this here. This is a velocity image. You can see this very tight area of rotation, gate-to-gate shear that triggered this tornado warning. Over here, this image is called a storm relative velocity product. And what this is it's a velocity product from the radar. And what the computer does is it takes away the forward motion of the storm. So what you're seeing is basically raw wind and how it's different from the area around it minus the motion of the storm. So you can see here, this is a very good indicator of a tornado at this location, because this wind is all moving in one direction except for this little pocket here. And with how close it was to the radome, with the radome being right here, it's only very, very short distance. That was actually a confirmed tornado. This is another Charlotte Tower Doppler image, velocity image. This one here spurred up right about the Cleveland-Gaston County line and moved directly east. Actually, this was Old Post Road? Nope, south of there. I can't remember the road name. We went out there and surveyed some of the damage, and it was definitely at least an EF1. It moved almost due east from this location. You can see tornado reports in Gaston County that came later. This storm here moved directly east along the state line, set off tornado sirens in York County, Gaston County, Mecklenburg County, moved east, came down out, touchdown right about here, moved across Pineville, went out into Mint Hill, did some pretty good damage in Ballantyne. There was actually one of our local TV meteorologists was live from his backyard and from his street showing the damage to the trees and the houses over here in Ballantyne, very heavily populated areas. causing lots of damage over here. Thankfully, there was no injuries on this side of the state, or at least on the North Carolina side. You can see here, this was out of Gaston. No, this was Spartanburg. This was Spartanburg County. Emergency manager reported extensive damage. Tractor trailers flipped over, buildings collapsed. Debris signature was observed, so it was likely a tornado. It was actually radar confirmed tornado because there was a debris ball in the tornado. They opened shelters. EOC went activated for that. That was a pretty big deal. This one was that storm when it moved into Gaston County. Amateur radio reported the tree down on the house in Gastonia, likely due to a tornado. Those reports came from us. I spoke to that Skywarn spotter that put that report in. He got that report because his neighbor was on the phone with somebody when it happened. He went over there and took a look. The next block over, he went over and took a look, identified the trees down, identified the pattern that took, and reported that to the Skywarn net as a tornado. And while everybody was talking about the tornadoes in Ballantyne and how it went all the way out through Mint Hill, major urban area, lots of damage, fascinating, miraculous. Here in York County, right here in Fort Mill, South Carolina, that storm proved fatal. It took down a tree, and an older lady drove into that tree, and it took her life. So this is not something that you see about, you read about, and you hear about happening other places. It's not something that, oh, that's a coastal problem, or that's a problem for the Midwest. This is happening here in our county. That led to me doing some research. 2020 tornado fatality statistics. These have been updated. The last time I had this data, it ended in August. This is the full year. This kind of changed a little bit, so we're going to go. This was my guess in the top 5. If you've seen this presentation before, you know how this plays out. My top 5: Oklahoma, Kansas, Mississippi, Arkansas, Missouri. Those are my top 5. The final statistics for the 2020 tornado fatalities: Tennessee ended up with 27. I believe they had 28, but they took one away from tornado fatality because the preliminary report was tornado, but they later went back and determined it wasn't. They took the top spot last year. They had 25 in one single event. That was a devastating day for the state of Tennessee, and for most of the East Coast. Mississippi put 12 on the board. Georgia edged us out. They got another one late in the year, and that gave them the advantage over us. We ended up with 8 total. 3 or 4 were from one event, and then Alabama brought up 5th place with 5. This year, it is currently February 23rd. This year, North Carolina has taken the cake, and they are running with it. They had 3 just last week in one event down in Brunswick County. So they're already out ahead of the pack. I think Alabama has 1 pending the investigation and the confirmation of it. But we're already off to 4 just in the southeast this year. It's serious. So I highly recommend, if you're not already credentialed as a Skywarn spotter, go to skywarn.org, I believe it is, or just Google online Skywarn training. There's a program through the National Weather Service put on by another company that offers free training. It's a 2-part course: the role of the Skywarn spotter and the radar interpretation basics, or convective basics. They cover very briefly about the radar, but they go into how storms build, why they do what they do, and how they do it. It's awesome course. Take it, get certified. Part of that process is letting your National Weather Service office know that they have you as a resource and putting your contact information in the event that they need you. I know Columbia does it all the time. After severe weather moves through the Midlands, their forecasters and their meteorologists are on the phone with ham radio and with our Skywarn spotters. Hey, this came through near you. What did you see? And they solicit those reports from the community. It's a little different now with social media and being instant. You can instantly at National Weather Service and tweet it right to them, and they can see it. Join in on Skywarn nets. Our Skywarn net control operators have access to the NWS chat, so they can directly message with the meteorologists, and we get information in return that we then disseminate. We had one during either the January or the February tornadoes last year. The National Weather Service, I was the net control station, they reached out to me, hey, do you have somebody that can put eyes on this? We can't tell if this is a funnel cloud or not. We don't know what it's doing. And we put the call out over the repeater, hey, does anybody have eyes on this? And one of our ham radio operators said, hang on, let me get my drone. Put his drone up and took 4K video of that thing rotating, tweeted it to the National Weather Service, and made it happen. So as always, if anyone has any questions, my contact information is up. Feel free to shoot me a text message or an email, give me a phone call, and we'll figure out what you need and we'll make it happen. Thank you.
On the air, calling CQ 20 meters.